So what I'll be talking on today is study of closed ideals and the bounded operators on LP space, and anything new I say will be joint in two papers under preparation. One is with Gilles Pizier and Guidon Scheckman, and the second one is with Chris Phillips and Guidon. There won't be too many definitions in this talk. The main definition is that L of x is my notation for the bounded linear operators on the Wiener space X. Notice I wrote Banach space X. I was tempted to write Wiener space X because they used to be called Banach Wiener spaces a long time ago. But since everyone calls them Banach spaces now, I just left it this way. And I want to point to one very old paper by Berkson and Porter in 1969, very old, it's 50 years old, in which the foundational work on the structure of ideals and bounded operators on Banach spaces was studied. And it's a very old paper, but if you think about it, this paper came rather late. In the Banach algebras had been studied a long time before, very intensely by, of course, by Gelfand, and then Murray and von Neumann developed it in the context of von Neumann algebras. C-star algebras was already a highly developed topic. So to have a foundational paper at this late date, I think is a little bit surprising. So I won't refer explicitly to results in this paper, but a lot of things I say do actually stem from this. The model for LP I'll be using is either LP on the unit interval or LP on the Cantor set. So these, of course, also are LP on groups, and you have Haar measure on the unit circle, or the unit interval, and you also have Haar measure, which is just the product measure of where you put probability of -1 and probability of 1/1/2, and you take the infinite product measure, will be Haar measure there. It's a little bit more convenient for certain things to work on LP of this group rather than this group. It's a much simpler group. It doesn't matter for the purpose of talking about this Banach algebra, because these two Banach spaces are isometrically isomorphic, right? If you take LP of any separable, purely non-atomic measure space, then it's just LP of it is just isometrically isomorphic to LP of the unit interval. Now, I'm not sure I really have to motivate studying the space of bounded operators on LP, but okay. To study it, sometimes this button doesn't work quite right. But let me say it. C-star algebras, I think, are clearly the most important non-commutative Banach algebras, and they've been studied for a very long time. After them, I think you can make a very good argument that the bounded operators on classical Banach spaces, in particular LP and maybe spaces of continuous functions, would be the most important one. Second reason, which is a pure math reason, is this, that if you look at the bounded operators on LP as a Banach algebra, its structure for P different than 2 is very, very different from the study of the Banach algebra structure of the bounded operators on Hilbert space. Now, the bounded operators on Hilbert space, capital L2, is the same as, of course, the bounded operators on little L2. And it turns out that the structure of the Banach algebra of operators on little LP is very similar to that on little L2. But as soon as you go to the capital spaces, you have this complete difference, as I'll try to indicate. And of course, there are some connections to harmonic analysis anytime you're studying properties of LP. Many people would argue, in fact, that the study of the Banach algebra bounded operators on LP is harmonic analysis. But if you don't believe that, it's certainly connected. Now, I'm letting P vary in the range between 1 and infinity, I don't need 2 here. And if you look at for different values of P, it turns out that although the Banach algebras, you might say, look similar, as Banach algebras, they're completely different. Now, the natural morphisms between Banach algebras are bounded linear operators, which are multiplicative. That is Banach algebra homomorphisms. And you can't get any from LP to LQ, no matter what the measure spaces are, with one tiny little exception, And that one exception is the case where P is 2 and Q is in the reflexive range. That's the only exception. And the reason that's an exception is that Hilbert space, infinite dimensional Hilbert space, is even isometrically isomorphic to a complemented subspace of LP. Well, that means that the bounded operators on Hilbert space can be modeled as a subalgebra of the bounded operators on L2. It's not just a sub. But for other values of P, you simply can't get any non-zero algebra mapping. So if you're trying to look at homomorphisms from Banach algebras on LP to Banach algebras on LQ, necessarily you need to keep P and Q the same. And that's even if you allow a change of measures here. So here's a proposition that's certainly partly known, I think not completely known until recently. Suppose you take a non-injective homomorphism that's not zero. I didn't say that, but I mean not zero, otherwise it's trivial. And suppose the first space is either a little LP space or LP of the unit interval of the Cantor set. Then this other space, Y, can't be a separable Banach space. In fact, it must have density character, at least the continuum. It's a little surprising if you think about it. Here you have, from this bounded operators on a separable space, all you do is say, well, you have a non-trivial kernel for this homomorphism, and this forces this other Banach space to be highly non-separable. Now this for P equals to 2, this is known. In fact, this was in Compton's original paper. You see, if you look at the kernel of a non-trivial homomorphism, of course, it's a closed ideal, right? The kernel of a homomorphism has to be an ideal. And it has to be closed because these are bounded linear operators. So it has to contain the smallest closed ideal. Now, if you take any non-trivial ideal of operators, it has to contain a rank 1 operator. That's easy from the ideal property. Therefore, it contains all finite rank operators. Therefore, it contains the closure of the finite rank operators. And on any reasonable Banach space, the closure of the finite rank operators is just the compact operators. It just requires what's called the approximation property, which all the LP spaces have. So we sometimes call these Kalkin algebras the bounded operators modulo the compact operators. They're called the Kalkin algebra when P is 2, but in this more general context, we call them Kalkin algebras. They have no non-zero representations in L of Y for Y separable. Y must have density character, at least a continuum. On the other hand, there are some positive results that you can talk about. Yes. I'm sorry. I want to say something about the proof of this theorem, because this is the only thing that I'll talk about for a proof. So here's the lemma to prove this theorem. Suppose that you look at little LP or LP of the unit interval or the Cantor set, then you can get contractive projections, contractive idempotents on the spaces, so that for any two different ones, the composition of the two is a finite rank operator. And the ranges are all isometrically isomorphic to whatever the domain space is, little LP or capital LP, okay? So if you assume this, then you can take these idempotents and send them over to L of Y, where you have this representation or this homomorphism range. And then the representation, or the homomorphism pi, has to map the composition of any 2 into 0, right? Because it's a non-zero homomorphism, so it has to kill the ideal of compact operators, and finite rank operators are compact. So the unit spheres of these spaces are disjoint separated subspaces of X. Notice that pi of P alpha cannot be 0. right? Because the ranges are isomorphic to the whole space. And that would mean the identity operator was in the kernel of the homomorphism, so it would be the zero homomorphism. But I'm assuming this is not the zero homomorphism. So the lemma very easily implies this theorem. Now, how do you prove the lemma? Well, I'm a teacher. What can I say? I give homework problems even in topics courses, and so let's call this a topics course. So I'm giving this as a homework problem, but I'll give hints. The first hint is a fact that everyone should know. If you don't know this fact, then you definitely want to learn this fact, that you can find a continuum number of subsets of the positive integers so that the intersection of any two is finite, almost disjoint. And then once you have that, it's very easy to prove this theorem for this lemma for little LP, right? Because you just take these projections to be projections onto LP of these infinite subsets. And for capital LP, it's also very easy, but I'll give you a hint for that. This representation of capital LP makes it very easy. If you try to represent capital LP as LP of the unit interval, it may take you a while to prove it. Now, so if you're going to talk about homomorphisms, say from LP into some LP of some measure space, like we were talking about in the previous space, you want to know, well, are there any there? And here it turns out that there are some. In fact, if you go back to Carlton's original work, what he proved is that you have an isometric representation of the bounded operators on Hilbert space over the compact operators, that is the Carlton algebra, into the bounded operators on some non-separable Hilbert space, which has to be at least as large as a continuum, density character or dimension at least as large as the continuum. Now it turns out that if you really understand Carlton's proof, you can prove that also for little LP. It's also true for capital LP. This was proved, I think, I'd like to know if anyone else has seen this result. It's a special case of a lemma in a paper that my former student, March Bowden-Harjo, and I wrote in 2015. It was we were doing something in a more general context, but I don't think it was known for what we did for LP up until this time. What's still open is whether you can get for capital LP the same result for little LP, where this Banach algebra isomorphism is actually isometric rather than just isomorphic. That's an open problem. So I mentioned Carlton and March Bowden-Harjo and myself, but there's another proof that Bletcher and Paulson came up with last year. They weren't aware of our paper when they did this. And the two proofs, the one that March and I did and the one that they did, uses very natural left approximate identities for these ideals of compact operators on the spaces. If you don't know what left approximate identity is, I'll tell you later. But then the further techniques that March and I used was ultra powers of Banach spaces, which has become a standard tool, also used in C-star algebras. While Bletcher and Paulson did a different argument where they went to the second dual. If you have a Banach algebra, there's natural multiplications on the second dual, the Arens multiplication. And before someone corrects me and says, well, there are two Arens multiplications, right? There are two Arens multiplications on the second dual, but sometimes there's only one, and we're in that situation here. So this raises a natural question. Look at other closed ideals in the bounded operators on LP. First of all, are there any? And for which the bounded operators on LP modulo the ideal is Banach algebra isomorphic to a subalgebra of LP of mu, for it has to be a non-separable LP space. That's why I say LP of mu. Now notice this question is meaningless in bounded operators on little LP because there's only one closed ideal of the compact operator. So this is definitely a question only for capital LP. Of course, there's a more basic question that we have to come to. Well, in the bounded operators on capital LP, What are those closed ideals? Are there other ones other than the compacts? And we'll see in a moment that there are many. So one of the main results of this joint work that Chris Phillips and Gidon Sheckman and I did is that if you look at the bounded operators on capital LP, the only closed ideal that has a left approximate identity is the space of compact operators. So this means that the techniques used to prove this theorem stated at the top, we start with left approximate identity. You have to find a replacement if you're going to get any positive result here. In fact, this is why we ended up proving this negative result. But the negative result is also a bit interesting. For one thing, we don't have any classification of these closed ideals. No classification at all. I don't think there will be one in my lifetime, probably not in yours either. And yet you can prove that none of them have left approximate identities. So this is not a new problem. I'm not quite sure how old it is, but at least it appears in the paper in 1996 by Christian Lemredi. He proved that something that's a positive result, that if you have any closed ideal in the bounded operators on LP, then there is an isometric even, algebra isomorphism, into the bounded operators onto some Banach space. Well, that's trivial. But that Banach space can be taken to be a subspace of a quotient of some LP space. But unfortunately, subspaces of quotients of LP spaces, when P is different from 2, are very, very different from LP. When P is equal to 2, you see you don't have a problem here. But when P is different from 2, you don't get LP itself. Now, we can't solve this problem for any ideal other than the compact, so it's wide, wide open. But now we come to the really fundamental result. What are the closed ideals in the bounded operators on LP? There's more than one if you get away from P equals 2, but what are they? Well, let's first think about just the case of the bounded operators on a general Banach space and how you can build ideals in there. So of course, if the space has the approximation property, as I said, you have a smallest one, the compact operators. If it fails the approximation property, the smallest one is the closure of the finite rank operators, but we're dealing with good spaces here. Another way of building them is to look at the weakly compact operators. These are operators that take the unit ball into a weakly compact set instead of a norm compact set. And if you have a non-reflexive space, this is another proper closed ideal. Of course, if the space is reflexive, well, if and only if the space is reflexive, this is all bounded operators because there the unit ball is weakly compact. Now, important one is the ideal of strictly singular operators. These are the operators which are not a Banach space isomorphism when restricted to any infinite dimensional subspace. Now, if you come from a pure Hilbert space context, you don't talk about these because they're just compact operators. But as soon as you go to spaces like capital LP for P different from 2, there are lots of strictly singular operators that are not compact. They're very, very important because they have exactly the same spectral, a strictly singular operator is exactly the same spectral theory as compact operators. The Riesz theory goes over to strictly singular operators. This was proved by Kato when he introduced this class of operators in order to study perturbation in PDE. Now, of course, if you're interested in any ring, you want to know that's unital, you want to know what are the maximal ideals, right? That's maybe the most fundamental thing to look at, because every ideal is contained in a maximal ideal. And here, when you look at a maximal ideal in just the algebraic sense, they will be closed because the invertible elements in a Banach algebra are an open set. And the closure of ideals and ideals. So these maximal ideals are automatically closed. But you'd like to know what are the maximal ideals in the bounded operators on X. And maybe there's even the largest one, at least sometimes. So here's a candidate for the maximal ideal in the bounded operators of X. You just look at all the operators on X so that the identity does not factor through it. So if you look at an operator in X, the identity doesn't factor through it, then it generates an ideal, and it will generate a proper ideal. Now, notice that if you multiply an operator like this on the right or the left by a bounded operator, you get another, another operator like this. So this operator is closed on multiplication on the right and multiplication on the left by bounded linear operators on the space. Okay? Now it's not clear that it's closed under addition. So it doesn't have to be an ideal. In fact, it's easy to build examples where it's not closed under addition. But if it is closed under addition, then it's an ideal, and it's clearly the largest ideal, because any operator not in there has the identity factoring through the operator, and so you get the identity in the ideal, so you get everything in the ideal, right? So it's not a proper ideal. Now, it turns out that when you look at the LP spaces, M of X is closed under addition, so, and you can even say more about it. So this was proved by Influence Starbird for p equals 1 and Moray, Sheckman, Free, myself for the other values of p way back in the 1970s. And there's another interesting localization of the concept of strictly singular operators. Strictly singular means not an isomorphism on any infinite dimensional subspace. But maybe you have a certain preferred types of infinite dimensional subspaces for which it's not an isomorphism, other ones it is. For example, then you have a localization of this concept. So you call an operator Y singular if it's not an isomorphism when restricted to any subspace that is isomorphic to Y. Now, if you look at the operators that are capital LP singular on LP, that turns out to be the same as this M of X. That also is not obvious, but it is contained in these theorems I mentioned. So I say it's a localization because if you look at a strictly singular operator, that's the same as being Y singular for every infinite dimensional Banach space or every infinite dimensional subspace of your domain space. It's the same. Well, of course, you want to mod out your maximal ideals and find out what you've got. I can't tell you anything. Other than it embeds as a subalgebra of bounded operators of some non-separate LP space in the special case where p is equal to 2. In other words, I know as much as Calkin knew long time ago. Here's another way of building an ideal, not necessarily closed, but we will take its closure. Just take an operator between a couple of Banach spaces and look at calligraphic subview, be all of the operators on your Banach space X that factor through this operator. Okay. So then if you multiply on the right and the left by bounded operators on X, you get something back in here, obviously. So if IU is closed under addition, this will be an ideal, not necessarily closed ideal. So how can you guarantee this is an ideal? Well, to make it closed under addition, the easy way is to make the direct sum of this operator with itself factor through the operator, which is easy to rig up operators that have this property. And this is what I'll mostly talk about. And then you'll have the closure of this ideal would be a proper ideal as long as the identity operator on X does not factor through U, okay? As long as the identity does not factor through U, then you can get a proper ideal, right? Because you won't get this. So these are the ways that you build these closed ideals. So let me just summarize the notation here. IU, all the operators on X that factor through this operator U. S is a strictly singular operator on X. Now a new definition. I haven't had a definition for quite a long time now. New definition. Ideal is small if it's contained in the ideal of strictly singular operators. And so that means in particular, all the operators in the ideal have spectral theory of compact operators. So you think you can handle them in one way. An operator is large if it's not small. So how do you guarantee that an ideal constructed of the form I of U is small? You just make sure that the operator you start with is strictly singular, because then you you look at all operators that factor through the strictly singular operator. They're all strictly singular. You take closure. The closure of the strictly singular operator is strictly singular, so that's all you have to do. How do you get one which is not strictly singular? Well, the natural way is to take some complemented subspace of X and to make sure that U plus U factors through U, just make sure that you choose one so that it's isomorphic to its direct sum. By the way, it was an open problem for a very, very long time whether every infinite dimensional Banach space was isomorphic to the direct sum of itself. And this was solved only in the 1990s by Tim Gowers on work that was part of a little bit of his Fields medal. I mean, it came out of what was the main part of his Fields medal. So it was a very, very difficult problem. So it's very difficult to construct Banach spaces that fail this property. And all the spaces related to LP that we know about have this property. So now, in order to guarantee that this is really a proper ideal, you just make sure that this subspace Y does not contain a complemented subspace isomorphic to the whole space. This has to be a little bit smaller than the whole space, that's all. Now, of course, it's silly to write I sub Y. So I'll write I sub Y for these ideals. So I sub Y, calligraphic I sub Y will be all operators that factor through the space Y. What are the small closed ideals in L1? Because I want to talk about ideals in L1 to get to this work with Pizier and Sheckman. Well, you always have the compact operators and the strictly singular operators. Now in L1, turns out that the weakly compact operators form a small ideal. That is, they're contained in the strictly singular operators. L1's non-reflexive. If L1 were for P bigger than 1, weakly compact's the same as everything, so you don't get a proper ideal here. However, on L1, the weakly compact operators are exactly the same as the singular operators. You don't get anything beyond the strictly singular operators here. This is called the Dunford-Pettis property of L1. That tells you how long this theorem has been known. What about large closed ideals? Well, you have the largest ideal, which I've already mentioned, M of L1. And then smaller than that is all the ideals that factor through little l1. See, little l1 is sitting inside capital L1 isometrically, even as a norm 1 complemented subspace. So I sub little l1 gives you an ideal which is not contained in the strictly singular operators. Capital L1, you can't stick inside little l1 anyway. So it's different from the maximal ideal, and it's different from the whole space. I guess to show it's different from the maximal ideal, you have to do a little something. So these are, how many I have here? Let's see if I can count. 1, 2, 2, 3, 4. That's all that were known for a very, very long time. 4 ideals, at least that's more than the one that we have in Hilbert space, but it's still not very many. And I don't know who first asked this question, but Peach put in his book in 1979, it's kind of the main problem of closed ideals in L1 is whether you can get infinitely many. Okay, now, we've already talked about how easy it is to build closed ideals in L of X, but the hard part comes when you build 2 closed ideals, how do you distinguish? How do you know they're not the same? For example, in capital L1, you have the strictly singular operators, you have the weakly compact operators, but they turn out to be the same. Here's a more sophisticated example of that. Fix a P bigger than 1 and finite, and look at the ideals of operators that factor through capital LP. Okay? These are all different ideals. You can check this. But once you take their closures, you don't get anything new. Every weakly compact operator is in the closure of each one of these ideals. So looking at such examples, I thought for quite a long time that the real key, we have 4. If you can find 5, number 5, then you're going to solve this problem. So last January, Sheckman and I were working, and we were able to do this. And the ideal is a very easy one to talk about. You just take take a basis to basis mapping from little l1 into capital L1, where you map the unit vector basis of little l1 onto the Rademacher functions. The Rademacher functions are Bernoulli random variables taking on 1 and -1. Well, of course, to a harmonic analyst, better to describe it as you map onto a certain set of characters, and this set of characters is a Seton set, the most basic Seton set when your group is a Cantor group, right? I'll come back to that. It's with probability 1. So what the Rademacher functions are acting in the L1 norm just like L2 does. The characters are acting like an orthonormal series in Hilbert space in the L1 norm. So this is kind of looking at the formal identity from little l1 to little l2, but then you stick little l2 back into L1, so you have a little l1 to capital L1 operator. So we were pretty happy when we showed that this gave a new ideal, because we had an idea for how we built a lot that looked like this one but are different. So you can map little l1 into capital L1, where you map the unit vector basis of little l1 to something that acts like the little lp basis, where p varies between 1 and 2. And the natural model for that comes from probability theory, wherein instead of the Rademacher functions or Gaussian random variables, you take what are called p-stable random variables. That's what it does. So these ideals are indeed very different. But then working a bit, they gave the same thing. So at this point, we had increased the number of known ideals and the bounded operators on L1 by 25%. So at this rate of progress, it was going to be the end of the universe before we knew the answer to Peach's question. However, this fall in Berkeley, Pizier and Sheckman and I were all together for a while, and we were able to kind of soup this up and show that, in fact, there are lots of small closed ideals in the bounded operators on L1. Not just infinitely many, but even uncountably many, the continuum of them. I'd like to say something about, I'll say more about that later if I have time. So what about large ideals? Well, we don't have any new large ideals. So there's this very famous problem in Banach space theory, whether every infinite dimensional complemented subspace of little l1 is isomorphic, of capital L1 is isomorphic either to capital L1 itself or little l1. These are the two that are known. No other ones are known. And how do we build large ideals? We take a complemented subspace and look at all the operators that factor through that complemented subspace. So until we have more complemented subspaces, we don't know how to build large ideals. But of course, there may be many, many different ways of building large ideals that we haven't discovered. We just don't know how to do it. So the new ideals that we have is a very natural family. And it comes, you can use harmonic analysis to do it. You look at these ideals of operators that factor through a particular operator, I'll call it UQ, index between 2 and infinity, so there's a continuum of them. And what is it? Well, little l UQ maps the unit vector basis of little l1 to a set of characters. And that set of characters is what's called a lambda Q set. So lambda Q sets were studied in the 60s by Rudin. And what is a lambda Q set? It's a set of characters well, for q bigger than 2, it's a set of characters so that the LQ norm on the linear span is equivalent to the L2 norm. So there's a set of characters where the characters are acting just like an orthonormal series in a Hilbert space, but you're using the LQ norm. So the Rademacher functions are lambda q for every value of q, every finite value of q. So they're even what's called a Sedon set. Okay, everything from harmonic analysis here. And in order to do this, we use Bourgain solutions to Rudin's lambda q set problem. And what Bourgain did is he showed that for every value of q bigger than 2, there is a lambda q set that's not lambda q plus epsilon for any positive epsilon. That was Rudin's problem. And we need a few more properties than that, but this is the main thing that's needed. Now I have to confess, with truth in advertising, although I prefer the harmonic analysis point of view here, there were older results in Banach space theory from the 70s that you could use as a subset. But since you have Bourgain's results now, I would prefer to do it this way. Now, here we have uncountably many closed ideals, of course, but are they different? And the trick is to prove that they're different. And if possible, at the end of the talk, I'll say a little bit about how you prove that the ideals are different, or a lemma for proving them. What about large ideals in LP and small ideals in LP when P is different from 1? Well, large ideals we've known something about for quite a long time. Because way back in '75, Sheckman proved that you have infinitely many complemented subspaces of capital LP. By different, I mean they're not mutually, no two of them are isomorphic to each other. And all of them are isomorphic to their squares. So if you look at the operators that factor through one of those complemented subspaces and take its closure, you get a closed ideal, and they have to all be different. So that gave infinitely many way back in 1975. 6 years later, he and Bourgain and Rosenthal souped that up, and they used a transfinite induction argument based on some of Sheckman's arguments there, and something called the LP ordinal index, in order to soup that up to uncountably many Aleph 1. But maybe they're more than Aleph 1. If you're a set theorist, there's a lot of room in between Aleph 1 and the continuum. Most set theorists completely disagree with the continuum hypothesis, after all. Models of set theory in which it's vastly, vastly wrong are more interesting than models of set theory in which they're true. So this is far from getting the continuum. And it's more, in fact, it's open whether you can get more than that. But the interesting thing is, there may even be 2 to the continuum. We don't know there's a continuum, but maybe they're even the 2 to the continuum. You say, well, wait. LP is a separable Banach space. How can there be more than a continuum? There are only continuum many subsets. Oh, but we're talking the bounded operators on LP. That's highly non-separable. That's density character of the continuum. So maybe the number of subspaces is 2 to the continuum. Who knows? No one has any clue how to build that many large or small ideals. Actually, I think it's open whether there's any separable Banach space so the bounded operators on them have more than a continuum of closed ideals. Now, what about small ideals? Well, there's actually a considerable history of small ideals, most of which occurs in this century. But I won't give the history, just jump to the end, which was a theorem done by my colleague Thomas Schlumprecht and his collaborator Andras Sachs just this past year. I think it's going to appear in 2018, that you get infinitely many, and in fact a continuum of small closed ideals in the bounded operators on LP, where P is in the reflexive range, and of course different from 2. And their ideals follow the same kind of philosophy as what we did. They're all of the form, the closure of the ideals that factor through a particular operator U, and U is even a basis-to-basis mapping, as we did. And the basis-to-basis mapping goes from a little LR space, where R can change, to a suitably chosen natural sequence space that's just about natural. The interesting thing, one of the interesting things about their argument is that the basis for little LR is not the standard unit vector basis, but it's another unconditional basis. So if you look at Hilbert space, if you take an unconditional basis, let's say normalized, it's equivalent, it's a Riesz basis. It's equivalent to an orthonormal basis. But for other values of P, even for little LP, which looks a lot like little L2, this is not true. There are other unconditional bases for little LP, normalized unconditional bases. There are lots of representations. It's been known since 1960. And as I mentioned already, whether there can be more than a continuum of them is still open. No one really has any idea how to attack that particular problem. Okay, now I would like to say, I want to make sure I don't run long. You know, the worst thing you can do when you give the last talk of a conference is to, oh, can I have 5 more minutes? I promise you, I will not ask for 5 more minutes. I'll try to even finish 5 minutes before. Okay, so let's go back to this theorem done by Pizier and Sheckman and myself. Here's the lemma, the key lemma for showing the ideals are different. So the hypotheses here, well, 0 less than P less than Q because the proof works there, but think 2 less than P less than Q less than infinity because in the application, P will be at least 2. And suppose you have a set of vectors in LQ that satisfy this, I'll call it a lambda Q condition right here. See, what this says is if you look at a linear combination of those where the coefficients all have modulus 1, then you can upper estimate the norm by just looking at the L2 norm of those coefficients. Now in the application, the VIs are going to be characters. And there'll be a lambda Q set of characters. So in fact, we will have this for all linear combinations. But for the lemma, turns out you just don't need it. But think about lambda Q set here. Now, when you have a lambda Q set, you also know you have a lower estimate in L2 because these are orthonormal. Characters are orthonormal. So you have a lower estimate with the L2 norm of the coefficients. And that lower estimate goes all the way to L1 because by extrapolation, if you have the LQ norm and the L2 norm equivalent, the L1 norm is also equivalent, by extrapolation. And suppose you have an operator on L1 that maps these characters to functions that are bounded away from 0. Well, there are finitely many, but everything's quantitative. Then that operator has to have big norm. That's what this says. You cannot map in the L1 norm a lambda Q set of characters into an L1 space of very small dimension. Now, here, this L1 space, I'm thinking about L1 of the unit interval, but in fact, it can be L1 of a finite dimensional space because these characters, if you put them on the Cantor group, you can put a lambda Q set in Bourgain's proof, this is how it goes. You can put this lambda Q set into the group -1, 1, not going to infinity, but only going to the number of characters, capital N, to the Q over 2, okay? So if you think about this L1 space here of being of dimension N, capital N, to the Q over 2. So Q is bigger than P, and you're trying to map that into a lower dimensional one, just keeping the norms of this discrete set of just a very few vectors bounded away from 0, then that forces the L1 norm to be huge. Right? Q is bigger than P here. So this lemma kind of really surprised us. And this is one of these extremely difficult technical lemmas that takes almost a half a page to prove. But it's the key lemma. It really is. The key lemma for showing the ideals we construct are different. And although there's no harmonic analysis in the lemma itself, in the application, we're applying it to the VIs being lambda Q sets. So I want to go back to this other theorem, one of the main theorems in this work with Chris Phillips and Gidon Sheckman, where you show that the only closed ideal in the bounded operators on LP for P different, well, you can say P equals 2 here, that has approximate left identity is the compacts. So here's a definition of left approximate identity in case there's anyone still awake who doesn't know the definition. You just take a net of operators in your algebra A, so that when you multiply vectors on the left by these, that converges back to the vector for every vector in the space. Approximate identity. And the way we prove, well, one case, so there are many, it turns out that in order to prove this, before I do this, let me say, in order to prove the theorem up here, you have to break it into cases where P is equal to 1, because that's the non-reflexive case. You expect arguments for L1, bounded operators in L1 to be different, because they really are different kinds of spaces. And then a different argument for P between 1 and 2, and then a different argument for P being bigger than 2. And it's natural to do that. Of course, at the end, in the reflexive range, you also have no right approximate identity by duality, okay? Because you prove it on both sides of 2. So here is the proposition, one that is needed for one of those cases. Suppose you take the natural basis for the little LP direct sum of Hilbert spaces with their dimensions tending to infinity. Now, I was talking earlier about where Schlimprecht and Sachs used an unusual unconditional basis for little LP. This is an unusual unconditional basis for little LP. It's isomorphic as a Banach space to little LP. This has been known since 1960. And take a very familiar object, the normalized Haar basis for a capital LP. Okay? The most natural unconditional basis for capital LP. And then look at the natural basis to basis mapping from this sequence space into capital LP that maps basis to basis from this basis to the Haar basis. Okay? So just the basis to basis mapping. Then that extends to a bounded linear operator from this representation of little LP into capital LP. So the important thing here is that you have a bounded linear operator from little LP that maps the unit ball of little LP into something that contains the Haar basis. That's really the bottom line here, and this is one way of doing it. I'd like to know if anyone has seen this kind of lemma, because this is very similar. It looks a little bit similar to certain things that are known to harmonic analysts. But this particular one we couldn't find anywhere. And the proof is not a very surprising proof, and uses techniques that are used all the time. You dualize. You can prove it by duality if you want, because we're in the reflexive range. And then you do an interpolation argument. You don't use recent interpolation. You use interpolation that's been known for a very long time, though, between H1 and L2. So, although I've done my best not to give any proofs, I think what I've done is try to give very, very important ingredients of proof to the two of the main theorems. This theorem, which has this, and this preceding one. This, which I think is a lemma that's going to be used quite a bit. Even, I have some experiences with very simple lemmas turning out to be useful. And I don't think this will be as useful as some of them, but I really think it will be useful sometime. Thank you.